Okay, any questions at this point? Okay, so what I want to do in the rest of the lecture is talk about two major tools used for unconditional de-randomizations of your favorite algorithm. And these two tools are pairwise independence, k-wise independence, and the other one is called epsilon bias generators. And there's other generic tools you can try to use. I mentioned on the first board, which I erased, a tool called method of conditional expectations. There are other methods you can use to try to de-randomize your favorite randomized algorithm. But we'll talk about these two, k-wise independence and epsilon bias generators. Okay, so k-wise independence, I actually alluded to it slightly in like lecture 4 when we were talking about Chernoff bounds and the second moment method, Chebyshev and fourth moment method and such things. So we'll talk about it in a bit more detail now. So one way you can think about k-wise independence, this topic, is it's a property that a pseudorandom generator might have. In some sense, it's like a pseudorandom generator that fools a class of functions expressible by degree k polynomials. But I won't quite phrase it like that. And often this is enough to de-randomize your favorite, particular randomized algorithm you have at hand. Okay, so a pseudorandom generator mapping an L-bit seed to an n-bit pseudorandom string is, let me start out with the simplest useful case, which is called pairwise independence. It's called pairwise or two-wise independent. If for all two distinct output positions, I and j in your the pseudorandom string it outputs, if you focus in on any two output positions, and you look, when the seed is drawn at random, as always, at the output of the pseudorandom generator in position I and the output of the pseudorandom generator in position j, well, it should be the case that this output is the pair 0, 0 with probability 1/4. And it should be 0, 1 with probability 1/4, and 1, 0 with probability 1/4, and 1, 1 with probability 1/4. Okay, so for every pair of indices in the output that you squint at, when you pick the pseudorandom string, it looks like the uniform distribution on 2 bits, quarter, 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 quarter. Actually, this is a very wrong name. I had to write it because this is what people call it, but it's a bad name. It should be called pairwise uniform, because pairwise independent merely suggests that these 2 bits are independent. But the actual definition that people mean is not only they're independent, but they're also 50-50 bits. Anyways, people will say pairwise independent. They really mean this, that these 2 bits, the ith bit and the jth bit, are both independent of each other and uniformly distributed. And in general, this is just this pairwise independence is a property of like a bunch of random variables. I mean, if you have a bunch of random variables, you say they're pairwise independent if any 2 of them are independent. Okay, and this is not the same as them all being mutually independent. Okay, and more generally, this pseudorandom generator is called k-wise independent. And again, it's a misnomer. It should really be called k-wise uniform, but what can we do? If for all k distinct output positions, a similar thing happens. Namely, the probability, when you draw the seed at random, that g of si1 through gs position ik, probability that this equals a fixed vector of bits, b1 through bk, is equal to 2 to the minus k. Okay, so all k output positions should look like they're coming from the uniform distribution. And furthermore, I won't write further definition, but there's an analogous definition if G is a generator with range sigma to the n, where sigma is bigger than 2. Okay, I didn't define this, but sometimes you might be interested in pseudorandom generators that output n symbols that are not necessarily bits. Okay, so in this case, you can make the analogous definition that any k symbols in the output look independent and uniform. So, the idea is, like often when you're analyzing your random values algorithm and you have like n random bits that you're using, by assumption they're independent, and you use that fact in your analysis and you prove some conclusion. But often, you don't really need that all the bits are independent. If you squint at exactly how your analysis works, maybe it only needs that every pair of bits is independent. Or maybe it only needs that every 4 tuple of bits is independent. And in this case, you will be satisfied. Your randomized algorithms analysis will still hold if the random bits it use are merely 2-wise independent or 4-wise independent. And the good thing is, it's a known fact, which I'll talk about, that there unconditionally exist pseudorandom generators that are 2-wise independent or 4-wise or 10-wise independent with really excellent seed length, namely order log n seed length. So let me first I'll tell you the theorem, then I'll give you an example application, and then I'll talk about how the theorem is proved. So this theorem is due to Alon, Babai, and Itai in 85. Okay, it says for all k, that's the k and k-wise independence, and for all prime powers q, so you can see that maybe some algebra is going to come into this. There exists a polynomial time, deterministically computable, k-wise independent generator. And its seed length is actually with range, even with range sigma to the n, with seed length, let's just think of sigma as 0 and 1 for now. L being k over 2 log n, basically. Okay, so first of all, ignore that plus order 1. It's not a big deal. Also, mainly think about q, the size of sigma being 2. So it's outputting bits. And don't even get too excited about this like k over 2. Just think of this as like k log n. Okay? I just state this because it's even better. It's like k over 2. So for example, q equals 2, the main thing we care about, pseudorandom generators outputting bits. And with k like a constant, like 2 or 4 or 10, L is order log n. Okay, and order log n is like the seed length we like because it means you can then fully de-randomize your algorithm in polynomial time just by trying all possible seeds. So if you have a randomized algorithm and you, after staring at it, realize that it only requires the random coin flips it uses to be 2-wise independent or 4-wise independent or what have you, then you can efficiently de-randomize it. So let's see an example of a situation in which that occurs. And I'm going to go over this example kind of briefly, but perhaps you've seen it before, or at least perhaps you've seen the example before. So here's an example usage. It's on the topic of factor 1/2 approximating max cut. So I'll say what I mean by this. Okay, so max cut is a well-known algorithms problem. I hope you know. You're given a graph G, vertex at V and E. And your task is to partition the vertex set into two parts. I'll call it R and R bar. And what you want to do is maximize the number of cut edges, which I'll write as number of E from R to R bar. It's just the number of edges that have one vertex in one part and the other vertex in the other part. Okay, these are called the cut edges. Okay, it's a classic NP-hard task. And so given such a graph, finding the maximum cut is NP-hard. We don't expect to do it, but you might try to come up with an efficient algorithm that does a reasonable job of finding a pretty good cut. And there's a very, very classic, simple, super simple algorithm that does a kind of reasonable job of coming up with a big cut. And it's the most naive algorithm of all. Pick a random partition. And it's a fact that I guess we'll see, and it's easy to see, that a random partition cuts half of the edges in expectation. Okay, so if you just choose your partition totally at random, you don't even really look at the graph, then in expectation, the number of edges you cut is half of all the edges. Is that good? Well, it's better than nothing. It's pretty good. For a long time, actually, this was the best polynomial time algorithm for cutting as many edges as you could. And let's even see the proof of this fact. Well, let's say without loss of generality, the vertex set is just called the numbers 1 through n. And it's a randomized algorithm. And so let's imagine its random string, as usual, is called little r. And this is randomly chosen to be an n-bit string. Well, now we're in a nice setup. We have like one random bit per vertex. So we can use that to define our partition. So we'll put vertex I into R if and only if the random coin flip Ri is 1. And now let's just think about how many edges get cut by this algorithm. So the number of cut edges is equal to, well, the sum over all edges ij in the graph of, let's say, the indicator, the 1, 0 indicator that Ri differs from Rj. Right? This exactly says that in your random partition, I and j, vertices I and j are on opposite parts of the partition. Okay, so we can take the expectation on both sides. Okay, and by linearity of expectation, which holds for all random situations, independent, not independent, it doesn't matter, we get the expectation of this indicator. The expectation of an indicator random variable is the probability of the event being indicated. This is the probability over R that Ri does not equal Rj. Okay, which is just the sum over edges ij of half. Ri and Rj are random bits. The probability they are different from each other is a half. Okay, and therefore you get, well, the total number of edges in the graph over 2, which is what I said. In expectation, you cut half the edges. But now let's take a look at this analysis. Do we really need that the n random bits the algorithm used were independent? No. We didn't need anything about them here. That was linearity of expectation. And then the only thing we did was to assert that this random string R had the property that for any two fixed bits, Ri and Rj, the probability that they're different is a half. And unfortunately, I've erased it. But this is definitely true, provided the R bits are pairwise independent. That's almost exactly what it says. It says that, well, all the 4 possibilities here have probability a quarter. So in particular, the probability they're different is a half. So you can directly see that this whole analysis holds up. It's exactly the same if the random string R is merely pairwise independent, or 2-wise independent. Okay, and now this theorem assures us that we can take k to be 2 and q to be 2, And we can, by the theorem, can replace, random R with this pseudorandom generator G that takes order log n bits to n bits. Okay, and the expected value of the number of cut edges when you use a random seed in the generator and this output string is still the number of edges over 2, which I suppose by the probabilistic method means there exists a seed such that when you use that particular seed, the number of edges cut will be at least size of e over 2. And so if you just try all seeds and see how many edges get cut by each of these pseudorandom generator outputs, at least one of them will give you at least half the edges. Okay, and you can try all the seeds in polynomial time. Does that make sense? Okay, so that's an example of just noticing that your algorithm really only needs pairwise independence. Let me give another sort of brief example. Well, let me leave it at that as an example. But let me say one thing that we talked about in lecture 4 is things that often if you have a sum of random variables, you're very interested in controlling the probability that they're far from their expectation. And we saw various tools for doing this, like Chebyshev's inequality and Chernoff's inequality and so forth. And one comment I made then, which you can think about, is that if you have a sum of random variables, the variance of that sum, it's the expected square of the sum, which if you expand it all out, involves expectations of products of pairs of variables. And therefore, the variance of a sum of random variables is unchanged whether those variables are truly independent or merely pairwise independent. Which basically means, as a rule, since the variance is the only thing that goes into, let's say, Chebyshev's inequality, it basically means, as a rule, if you're ever analyzing your algorithm using Chebyshev's inequality, typically you'll find that the analysis holds up exactly the same if your random bits are merely pairwise independent. Okay, and you can use this generator in that case. Or for fancier things, we saw the fourth moment method, which sometimes gives better bounds, and that will hold up if your random variables are only 4-wise independent. Okay, but Chernoff bounds, for example, typically need that the variables are truly independent. But if you're using a weaker thing like Chernoff, then often pairwise is enough. Okay, so let's see a little bit about how we would prove this theorem. Here's where we'll start seeing connections to algebra and codes. So let's think about this particular theorem in the case of q equals 2 and k equals 2, which is the most basic and interesting case, pairwise independent bits. So consider the following pseudorandom generator, G, which maps L bits to n bits, where n is 2 to the L minus 1. So that's a great stretch. It's taking log n bits to n bits. And it works by taking the seed S and mapping it to, well, the row vector S times this matrix that we saw before that has all the binary strings, except for the all zero string, written as its columns. And this is all over the field of size 2. So everything is mod 2. So this, when you multiply it out, gives you a length n row vector R. Okay, and it maps L bits to 2 to the L minus 1 bits. So every possible binary string except the all zero string. And the claim is that this is 2-wise independent, or pairwise independent. And if this claim is true, then we've proven the theorem in this case. It's great because we've mapped log n bits to n bits. It's pairwise independent. This is certainly efficiently computable. You just write down this matrix and do the multiply. So let's think about why it may be pairwise independent. So what do we need to do? We need to focus on all pairs I of j of output positions here and argue that when okay, this matrix is fixed. When S is chosen at random, these will be 2 random bits. And we just have to argue that, we see the 4 possibilities with probability 1/4 each. So what are these 2 random bits? Well, it's just S times like the ith column, or dot the ith column, and S dot the jth column. Okay, and really all we're going to use about the ith and jth column here is that they're not the all zeros column, and they're distinct. Okay, in fact, we're going to use that, that these 2 columns are linearly independent, 2 linearly independent vectors. Although it's a very pathetic statement over F2 to say that 2 columns are linearly independent. It just means they're distinct and not 0. But I'm going to leave this as an exercise for you. If you do, S dot some columns, this, I guess 3 in this picture. If these are linearly independent, and this is, truly uniformly random, then these 3 bits will be uniformly random. Okay, so this is not a very hard exercise. I mean, you can think of, in this particular case, if you have just 1 column, as long as it's the non-zero column, if you dot a fixed non-zero column with a random vector, you get a random bit. Now you have to think about, like, let's say if this is another distinct random vector, you dot it with this truly a distinct fixed vector. If you dot it with this random vector, not only will it be random, but it'll be independent from this guy. It follows from the fact that the difference of these 2 columns is not the all zeros column. Great. So in some sense, when we're proving this claim, what do we really rely on? I said that we really relied on all pairs of columns here are linearly independent. And if you think back to the last lecture, hopefully you remember that, really, the least number of linear dependent columns in a matrix is equal to the minimum distance of the code for which this is the parity check matrix. I don't know if you remember that fact from last time. But really, what we've relied on in this claim is that the dual code, okay, this was really the generator matrix basically for the Hadamard code. The dual code, which is the Hamming code, has minimum distance, 3, if you recall, in particular greater than 2. And actually, this gives us this idea, basically, this fact that, if you have linearly independent columns, then these output bits or symbols will be uniformly random, together with the characterization of like the largest number of linearly independent, the characterization that the minimum distance of the dual code is like the size of the shortest set of linearly independent columns, gives us a general way to construct k-wise independent generators. Okay, so sort of a generalization of this exercise is that if you take x, a vector of length L over a finite field Q, and you map it to x times G, a vector of length N, this mapping is k-wise independent according to this definition, if and only if the dual code, G dual, has minimum distance k, greater than k. Okay, and so if you know good codes, then in some sense their duals give good k-wise independent generators. So sort of like a corollary and final exercise for you. If you use Reed-Solomon codes, you get pseudorandom generators that are k-wise independent and have seed length basically k log base q of n. Maybe plus order k here. OK, so really just using this fact and plugging in what you know about Reed-Solomon codes, you basically get this theorem, except you have k here instead of k over 2. But if you're like really enthusiastic about getting the best possible parameters, then you can use the dual of the BCH codes, which are a little bit better, and that's what gives you k over 2. OK, but this is good enough for almost all practical applications.